Hi, my name is Stuart Yoder. Welcome to the session Firmware Standards and Security. Our agenda for today is to talk about a new spec called the Base Boot Security Requirements. But first, I'm going to talk about some of the context of where this spec fits into other ARM standards. It's part of the SystemReady set of documents. And so I'd like to begin by giving you an overview of what SystemReady is, and so you see where BBSR fits into that. We'll then talk briefly about a new architectural compliance suite that is available to test compliance with BBSR, and then finish with kind of relating how these requirements fit with platform security more generally, and how, as far as assessing the security of a platform. So to start, SystemReady is a certification program from ARM that has the goal of making software just work on ARM devices. You can see in the kind of middle of the screen, there's the more traditional approach that we've seen, in the past has been that in embedded systems, you have hardware, firmware, and operating system that are fairly tightly integrated and kind of in a vertical stack where every silicon vendor has unique firmware and quite possibly an OS that's closely coupled to that. The goal of SystemReady is to allow standard off-the-shelf OSs, like, for example, Ubuntu or Fedora, to run out of the box on top of a compliant system, compliant firmware and compliant hardware. So that's the goal, is to have software to just work. There are several bands of SystemReady, SR for servers, ES for embedded systems, and then IR for IoT ready devices, and then LS is for Linux boot based systems. And the goal is to have across different market segments, these standards in place so that, regardless of where you are in which segment, that these standards will let you run off-the-shelf OSs, just saving lots of time and engineering effort. The number of specifications that are part of SystemReady, BSA specifies hardware requirements. There are some hardware supplements for servers, for example. There's a server supplement that describes additional server requirements above and beyond BSA. BBR specifies firmware requirements for firmware interfaces, and that includes UEFI interfaces, ACPI, and SMBIOS. So the BBSR, the Base Boot Security Requirement Spec, is part of this family of documents and adds security interface requirements for firmware. And so it's essentially an extension to BBR, but adds additional security requirements that are specific to security interfaces. There will be a compliance badge that we are currently calling the security extension, that addresses this area of security interfaces. And so for systems that comply to BBSR and pass the associated ACS, they can receive the security compliance badge. And we'll talk a little more about, again, what these requirements are, about the ACS that is used to test it, and where this fits. So the Base Boot Security Requirement Spec is, again, focused on the interface between the OS and firmware, and specifically the security interfaces that are not covered by the other specs. There are three main areas covered by the spec. It's a fairly short document, but there are authenticated variables and UEFI Secure Boot, and then firmware update using update capsules. And then lastly, for systems with TPMs, there's the TCG2 Protocol and TPM-based measured boot. There's a link there to the BBR spec if you want to dig into the details of what the spec says. So we're going to next talk about each of these areas and what the spec, what we're getting at in the spec, for these different topics. So to start with, Secure Boot. So most of you are probably familiar with Secure Boot. It's a process by which, when you start from coming out of reset, every component as you go through your boot flow, the different firmware components all the way up to the OS are verified. And so before executing the next component, the prior component looks at the digital signature of that component and compares it with the actual image that's being loaded and can verify whether the hashes match and can determine whether it has integrity or not, or maybe has been tampered with. So that's a secure boot flow. And where standards come into this, as far as the BBSR spec goes, relates to the UEFI based firmware and how it manages keys. So there's a key hierarchy that's defined by the UEFI spec, which includes platform key, PK, the key exchange key, KEK, and then DB and DBX. And so this key hierarchy is how you manage keys. You can add new keys, revoke keys, and they're managed with UEFI variables, and there's certain requirements around how these variables are set and used and authenticated. And then during boot, as images are loaded, UEFI drivers, et cetera, they are validated against these keys. So that's one aspect of this, is just the variables, and then the management of them, and then the signing and validation of images. So there's requirements in the spec about these that you'll see. In addition, there is a firmware interface in the UEFI runtime services that is there to allow the OS to manage the secure boot keys. So in case you need to revoke a key or add a new key, there's a firmware interface that lets you do that. And so that's how the OS may need to access secure boot interfaces. Next topic is firmware updates. And so this is the process of how you update the system firmware in your system. And BBSR requirements apply to systems with OS-based or in-band firmware updates. If your system has a BMC or some other out-of-band mechanism to update the firmware, then these requirements don't apply. But if you are doing OS-based firmware updates, then the requirement is that you use UEFI capsules and implement these other firmware interfaces to do firmware updates. A UEFI capsule, as you can see on the left side of the slide, consists of a firmware payload, which could consist of multiple firmware images that are for your system firmware. There's some authentication info that includes a public key that's used to verify these images. And then a firmware management protocol header that describes the firmware that's being updated, and finally an overall capsule header. And so that's the format that firmware is expected to comply to in order to be able to, for the OS to be able to do updates. So the process is that the firmware vendor provides this capsule. The OS or firmware can use UEFI interfaces, like in number 1 here, the set image call, to send the image or communicate to the firmware that an image is ready to be installed. The firmware then authenticates the image using the authentication info, and then can write it out to flash. There's an FMP driver you can see in the system firmware block here, and there's a unique identifier called a GUID that identifies the capsule. It's in the FMP header, and that ties to the driver in the firmware that's going to be handling the update of this capsule. So that's how the firmware knows which FMP driver to use to do the update with. So the image is sent to the firmware updates it in Flash, and then there's a table called the ESRT that is another firmware interface that is the way the firmware publishes the current state of the system firmware. So you can have any number of system firmware components. They're advertised via the ESRT, and you can see the current version, what firmware is in the system. And so these are all the interfaces that are expected to be there in your firmware to support the firmware update requirements. The next topic applies to systems with TPMs. TPM is a secure element that has a number of security functionality, but the one relevant here relates to what we call measured boot. And so what that means is as you go through your boot flow, as each component loads the next component, it takes a hash or a measurement of that component and writes it into the TPM. And so there are special registers called PCRs in the TPM, and that's where these measurements are extended or stored, and they can then later be used for various security policies. For example, a common example would be you may have a disk encryption key stored in the TPM, and it won't be released for use to decrypt your hard disk unless the PCRs are in the correct state. And so it's a way you can detect tampered firmware, because if one of these firmware components have been tampered with, a hash would have been not as expected. Therefore, the value in the PCR would not have been what it was expected, and your disk encryption key would not be released. And there are other policies, using attestation and so on that you can also use for this. But measured boot is the process by which these measurements are made. And so there are a certain set of requirements that are defined in the TCG spec. I've listed it there at the bottom, the PC client specific platform firmware profile spec. And that spec defines what PCRs are supposed to receive, which measurements, what has to be measured. And so that is what BBSR points to define the specifics of how measurements are made. In addition to measuring code, there are also data objects that may be measured as well. For example, your secure boot variables, and maybe other security relevant data or state that may be measured as well. And so all that goes into the TPM. And then in addition to writing things to PCRs, there is a data structure called an event log, where the measurements and additional metadata are recorded. So this is in memory, so that it can be compared with the TPM later, and you can actually better understand what measurements went into the TPM. And so the standard as far as BBSR goes is about how to take these measurements, what needs to be measured, and what metadata needs to go into the event log are some of the key things that firmware has to comply with. Another TPM-related requirement relates to this protocol called the TCG2 Protocol. This is a firmware interface that firmware makes available to a firmware client, and it lets that client interact with the TPM and access the event log without having to have a TPM driver and so on. Let's see. So some of the key APIs in this protocol include the way to get the capabilities of the interface, get the event log, to extend new hashes into the event log and PCRs, and then to submit commands. And so one example of how this gets used is like a program like Grub, like a second stage bootloader, can use the hash log extend event API to compute a hash of, like, say, the Linux kernel that it's loading, and it can record that into the TPM using this protocol without having to have a whole set of TPM drivers in Grub itself. So it's an abstraction that makes it easy for programs like Grub to take measurements. Another place where this protocol is important is in getting the event log after all the measurements have been made. An OS like the Linux kernel needs to get the event log and make a copy of it so that it can be used, for later for OS purposes, or to make it visible to the users. And so there's this get event log API is the way Linux gets the event log from the firmware before it transitions to its kind of runtime state. This protocol is only available as a boot service. It's not available as a UEFI runtime service. And so, get log is one of the last things, get event log is one of the last things that the OS would do before transitioning to exiting boot time services, exiting boot services, and going on to runtime. So there is a compliance suite that is being made available to test compliance of firmware to these requirements. It involves several pieces. It follows the same structure as the existing ACS suites, if you're familiar with those. So there's a set of SCT tests, which are firmware-based tests, the UEFI self-certification tests, and that includes an existing authenticated variable test, as well as a couple of new tests for Secure Boot and the TCG2 Protocol. And then there's a Linux-based firmware test suite that has several security relevant tests that are part of the security ACS. And then a couple manual test procedures include firmware update, where the vendor provides an update capsule, and there's just the manual process of doing a firmware update. It's kind of hard to automate that one. And so this just involves going through the firmware update process using a vendor provided firmware update capsule. For TPM measured boot, this involves an analysis of the TPM event log from the measured boot run. And so it's just to look at whether or not the measurements required by the TCG spec are as expected. And so, but it's currently not automated. That may be coming in the future. So that's the set of what's in the ACS. There's a beta release now available. There are links here to the pre-built image, which you can put onto a USB key and try out on the system, on a board. I guess the recommendation would be if you are already compliant with the IR or ES or SR bands of SystemReady, and that's kind of in good shape, then you would, as a next step, take the security compliance suite here and then run that. There's also links to the README and users guide as well. Finally, so we've talked about how BBSR has defined requirements around the security interfaces between the OS and firmware. And again, the goal is so that OSs just work. But what we're not assessing as part of the suite is the underlying security of the firmware or the system. We're not assessing the implementation of how some of these security interfaces were implemented. So the focus is on interfaces. And so questions like, how are your secure boot variables secured, and are they tamper-proof? Is their user interface into the firmware that's not password protected, that would allow an attacker just to go change things or turn off secure boot? What's the behavior if during secure boot, the image validation fails, and our best practice crypto algorithms in use? These kind of assessment questions is really part of a security assessment program, similar to the PSA, the Platform Security Architecture Assessment. And so the goal is, or the intent is that the SystemReady program, can be used in conjunction with a certification program like PSA to provide, certification of both the interfaces and the underlying implementation. PSA, just a little bit of background, I have a couple of slides on that, provides a set of security goals that, are congruent with the SystemReady program, but this focuses on the actual implementation, and there are questionnaires that have to be completed to kind of show that you've done this in a secure way. There are several different levels of certification with PSA, level 1, 2, and 3, and there are different parts of the system that can be certified as well. There's a silicon-based certification, another one for the system software, which includes the OS, and then there's device level certification, which includes the entire system as a whole. And so that's how PSA works. And there's a link on the previous slide to the PSA program. But in order to have a system be secure, you need some kind of assessment like this in conjunction with the SystemReady security assessment. I've listed a few resources here. Resources pointing to SystemReady, the BBSR spec, and then linked to the ACS. There's a couple of helpful security guides from ARM that provide guidance on hardware and firmware requirements for security that will help you with PSA certification. And then there's a link there to the PSA certification website as well. Thank you very much.